Dear students, welcome to the fifth lecture of the course. We have been talking about the basic techniques in information retrieval, and today we'll talk about the different types of indexes used in information retrieval system, and we will talk about the ranking of the documents in any IR system. There are several ranking techniques in IR systems, and today we'll talk briefly about one of them, which is vector space model. As we have discussed before, that every IR system has an index at its heart, and an index contains the terms along with the mapping of the locations in which they appear in the entire document collection. The index type we have been using so far is a flat index or a schema independent index that we have been seeing so far. There are many other types of indices that can be used for developing an index. Okay. Now, one of them, today we'll talk about three of the other techniques plus the fourth schema independent index. Now, any document oriented index, it can have two components. One, the document number in which the term appears, and second, an offset within the document. So what do I mean? Let's say let's talk about the 37 plays of Shakespeare. This is play number 1, this is play number 2, and so on and so forth till the last is play number 37. Now we can have a document number like this. 1 is the document number, 2 is the document number, and 37 is the document number. And inside that every document there are terms. So the first term we put document number, like document number is 1, and we put the term number, this is 1. Okay. Similarly, the second term will be 1, 2, the third term will be 1 colon 3, and so on and so forth. Let's say this is the last term, it is 1, let's say 123. Now the next document, when it starts, it will start with document identifier, which is 2, and the first term will again be assigned 1. Okay. So if you remember, if you recall from the previous lectures, in the flat schema independent index, we do not have document identifiers, and we keep counting onwards from the last word in the first document and the first word in the second document. They are continuous, the numbering is continuous. Here we again restart. Every document's first term is assigned 1, the second 2, and so on and so forth. Okay. So we have two components, document identifier and the offset of the terms inside that document. Now we have seen in the previous lectures that we always need to compare which location is smaller and which is bigger. So in a flat index, it's very simple. So every integer is smaller than the next integer. But here we have two numbers. So the criteria is, if I go back to the previous slide, n and m, these are two parameters. N is the document identifier and m is the offset inside the document. It is less than an other value, n prime, m prime, if and only if n is less than n prime. So first of all, we will see the document identifier. Like any position inside first document is smaller than any other position in the second document. So let's say if I have 1 colon 123, this second number is bigger, quite bigger, but in second document it is 2, 1. This second number is pretty small, but still our criteria is the first number 1, and here it is 2. So no matter what the second number is, this is less than the second number. So if the document identifier is smaller, then no matter what second value we have, it is considered to be smaller than another index in which the document number is greater. So the first thing to know which is smaller index value is the document identifier. A document identifier with a lesser value is considered to be lesser. And if in the second case, if and n prime are same, okay, if we are talking about the same document and n prime are same, it means that we are talking about the same document. Like in this case, 1, 1, and we have 1, 20. So now n and n prime, they are same. So this will be considered less than the other because of the second value. 1 is less than 20. So the simple way of looking at it is first look at the document identifier. If it is less value, then it will be considered less than the other index no matter what second value we have. And inside the same document, it's quite intuitive that the offset will decide which value is less. Okay. So like here you can see the first occurrence of first is in the first document at location 2205. The second is in the first document at 2268. Over here it appears in document number 22 in these locations, and the last is in document 37. Okay. If I look at any other index, let's say here, play, the last one. So the first occurrence is in document 1 at 40,508, and the second occurrence is at document 2, 35,070, and so on and so forth. So every index has two values, the document identifier and the number of the term inside that document. So now if I call first hurly-burly, it will return 930963. Hurly-burly, where's hurly-burly? Yeah, here. So the first occurrence of hurly-burly is in document 9 at 30963 position, and if I call this method last thunder, it will return 37125338. Thunder, where is thunder? The last occurrence is in document 37 at this position, and so on and so forth. Now before moving forward to the other type of indices, we define some basic terminology, and T defines a document frequency, okay, the number of documents in the collection containing the term T, how many documents contain a term T in the entire document collection. FTD is the term frequency, frequency of term T in D, LD is document length, L average is average length of document, and capital N is the document count, the total number of documents in the entire corpus. Now there are different types of document-oriented indices. We'll talk briefly about them. We have doc ID index, frequency index, positional index, and schema independent index. So doc ID index, for each term it contains a document identifier of all documents in which the term appears. So it simply contains the document identifiers. Where it appears inside the document, this information is not there in this type of index, only the documents in which the term appears. For example, let's say this is our document collection. Okay, let's say this is the document collection, a very simple small one. The first document contains do, you, qual, sir, 4 terms. The second document contains qual, sir, no, sir, and so on and so forth. So then for this type of index, doc ID index, for every term, this is the vocabulary we have discussed in the previous lecture. So all the unique terms listed in alphabetical order. So here A appears at position in the document 3, M appears in document 3. So A, it appears in document 3 over here. It does not appear in any other document. Do appears in 2 documents, in document 1 and document 3. So in document 1 it appears here, and document 3 over here. Okay. Similarly, sir appears in document 1, 2, 3, 5. Sir appears in document 1, 2, 3, and 5. all the documents except document number 4. So it contains the document identifiers in which the term appears. The first value in the index is the length of the list. In each case, the length of list is appended to the start. So how many items we have? Like here we have only one item. In this case we have 2 items. Over here we have 4 items in the list. So it is like the frequency of the term in the entire collection, or actually the length of the list. So how many entries we have? Here we have 4 entries, and so on and so forth. The second is a frequency index. Each entry in an inverted index contains 2 components, a document identifier and a term frequency value, right? The next index is an extended version of this. In the previous index, it contains only document and frequency. In this index, positional index, it also contains the positions of all those values in every document, right? So let's see how it works. Positional index, like the first is again the length of list. We can ignore this part. It is the length of list. Okay. So here it appears in document number 3. How many times it appears? It appears 1 time, the frequency in document 3, and at which position it appears at position number 13. For example, in document 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. In document 3, at 13 appears 1 times. Let's say I take this one, do, okay. So it has 2 values. In document 1, it appears 1 time at position 1. So in document 1, document do appears 1 time at position 1, and in document 3, 1 times at position 3. 1, 2, 3. Okay, I hope you get it. Okay. And the last one, schema independent index. It does not include the document oriented optimization. We have been using it in the last few lectures. So we start from first term in first document and we keep counting till the last term in the last document. So do is 1, this is 2, this is 3, this is 4, the squirrel is 5, 6, 7, 8, and so on and so forth, till the last value of sir is, I believe, 28, right? So here appears at position 1, M appears at 14, this 1923, and so on and so forth. So these are different type of indices that can be used. Each index will have its own application. We are not going into details to discuss them, but I hope you get a basic idea of the indices, what type of indices we have and what information they hold, and how to compare the values when we have 2 values, a document identifier and the offset of terms inside the document. The second topic we discussed today is the ranking or retrieval. What is ranking? Whenever we have any information retrieval system, when we retrieve the documents, we want to show the most relevant document at the top of our search results. The second document should be less relevant as compared to first. The third should be lesser, and so on and so forth. Till the last document, it should be least relevant to a search query, right? So there are many ways of ranking. Every search engine, it uses its own methods, and of course the Google, they have the smartest algorithms. They never share with the common public. They are the business secret. So, but we can always discuss some of the basic techniques. There are many techniques that can be used for ranking. The one we will discuss today is vector space model. There are models based on proximity, on Boolean retrieval, based on the probability, and so on and so forth. So the technique we are going to discuss today is vector space model. At the heart of the vector space model are the document vectors. Probably you will have studied in your high school that there are 2 types of quantities in math. We call one type as scalar quantities and the other are called vector quantities. the scalar quantities, they only have a magnitude or a value. Okay. Magnitude or just a value. The vector quantities, they have two things. They have a magnitude, a value, and a direction. Okay. So, like if I have a 2D vector in 2 dimensions, it has two components. One, like if it is V, vector V, this one is called Vx and this one is called Vy. Similarly, if I have a 3-dimensional space, a vector will have 3 dimensions. Now, as human beings, we can only perceive 3 dimensions, okay? But in mathematics, we can have n-dimensional quantities. We can have vectors with huge number of dimensions. So here in vector space model, every document is represented as vector, and each vector component corresponds to a term in the vocabulary. So how many dimensions we have for vectors in the vector space model? It is the same number of dimensions as the number of terms in the vocabulary, right? If you can recall, in the Shakespeare's 37 play, the size of vocabulary was something like 27,000, 28,000. I cannot recall exactly, but it was in like tens of thousands, right? So a document, when we represent it as a vector, it will have a component for every term in the vocabulary. Okay. Now, what is the basic idea? What is the philosophy behind vector space model? If we are given a query vector, so if we can represent a query as a vector, the user is giving a query, he wants to retrieve some information, the search results. Given a vector query and a set of document vectors, and we have many document vectors, we rank the document by computing a similarity measure between the query vector and each document vector, comparing the angle between them. So we compute angle between two vectors, and the smaller the angle, the more similar they are. Okay, like here we have many vectors. Okay, we have many documents. This is document D1 vector, this is document D2 vector. Now this query has vector Q. Now we measure the angle of query with document D1 and we measure the angle with document D2, and now the one which has a smaller angle, it is considered to be more relevant to the query. Like in this case, I can see with naked eye that D1 has a smaller angle, so D1 is more similar to query Q as compared to D2. Okay, so the math is very simple for this. If we have two V-dimensional vectors, okay, the number of dimensions are V. What is V? If you recall, the vocabulary, it contains all the terms in the unique terms, all the distinct terms in the document collection. Like I have a, I have am, I have Abbasis, if you remember, I have which, okay, I have, the last one was something like swaggered, if I can recall. Okay, so for every term there is a component. X1 refers to a, X2 refers to m, the third component refers to this, the fourth to this, and so on and so forth, till the last component, it refers to the last term in the vocabulary. Okay, so every component refers to one term in the vocabulary of the document collection. These are the distinct terms in the document collection, right? How we convert these words, all of these, they are words, but they are converted to numbers. So this, inshallah, we'll see shortly how to develop a vector, but for now let's hold on. So if we have two vectors, a vector for x and vector for y, let's say this is x is document vector and y is the query vector. Okay, so we can calculate the dot product by this simple formula. I'm sure you have studied it in your high school maths courses. X dot y, two vector dot product, can be calculated as we can calculate the magnitude of the vectors, okay, and the angle of the vector. Okay, so the dot product, it can also be expressed as this. So it is sum of product of all the components in the two vectors. Okay, so we have x1 and y1, multiply x1 and y1, then multiply x2 and y2, multiply x3 and y3, keep doing till the last term. Okay, so I can say the dot product, what does it mean? It means x1 into y1 plus x2 into y2 plus x3 into y3 plus go on, keep doing this till the last term, which is v, x v into y v. V is the size of the vocabulary. Let's say we have 28,000 terms, so it will be x 28,000 into y 28,000, right? And how we can calculate a magnitude? For calculating magnitude, we have a simple formula. Sum of square of all the components, and once we have got the sum, take square root of this. Like, what does this mean? It means x1 square plus x2 square plus so on till the last is x v square. Take this sum and take a square root. Okay, so we can calculate very easily. We can calculate the product of two vectors, and we can calculate the magnitude of two vectors. And if we insert these over here, like I can convert this into this. Okay, cos theta is here, and we have moved these towards this side and flip the equation, so it becomes x over x dot, okay, it moved here, and y over y mod. Okay, or in the next phase, what I can do, x dot y, okay, this one we can move this over here. Okay, x dot y is this, so we can replace x dot y with this formula, sum of product of all the components in x1 and in x and y. Similarly, for magnitude, I can take this formula, I can move it here for x, and similarly for y. Okay, so very simple formula, simple manipulation. And if we want to compare the similarity between two vectors, a document and a query vector, we can have d over d mod. Okay, how we can calculate d, we'll see inshallah, how to convert into numbers, and q into q mod. So if we want to calculate the product, if we want to calculate the angle between two vectors, we'll simply use, in fact, this formula. Okay, this is equivalent to this. So we'll just multiply all components together, add them up, and we will take square root of sum of all components of first vector and the second vector. It's not that complicated, it's very simple. When we solve a complete example, I hope that things will become very clear for you, inshallah. And I'm sure you have studied it in your high school as well. Now there is one question that may arise in your mind at this stage, that this vector space model, it is not efficient. Because for just 37 plays, we saw that the size of vocabulary was like 20 or more than 20,000. Okay, it was more than 20,000. So we have more than 20,000 values here, we have more than 20,000 values here. So if we have 37 plays and each document has more than 20,000 components, and then a query vector, it will also have more than 20,000 components. So you may think that it is a very slow technique, but actually no, it is not the case. Why? The query vector is sparse with all but a few components being 0. Well, the idea is that whenever you give query, query will have very few terms. Like if I give query William, Shakespeare and marriage, okay? Now we have only 3 components which are non-zero, all the other terms, okay? In this vector, all the other terms will be 0 except 3 non-zero values, right? So whenever we are calculating magnitude, we only need to take square of 3 terms and take square root. Similarly, whenever we are multiplying any vectors, we need to consider only those terms which are non-zero, and a query will never ever have thousands of components. So that is why in vector space model, although the size of vectors is very large, it can be in millions, because for only 37 plays the vocabulary size is in thousands, tens of thousands. So for any mid-size collection or a large size collection, we may have millions of dimensions. But whenever we are performing the calculations, the actual calculations are performed on very few components which are non-zero in the vector. Otherwise, most of the components, especially in the query vector, they are 0. So whenever we are processing, all the other components, they become 0, because whenever you multiply any value with 0, it becomes 0. So we do not need to consider the 0 values, just focus on the query terms and do all the calculation. That is why a vector space model, although the size of vectors is huge, still the processing required to calculate the ranking of the documents, it is pretty low. Okay, now let's come to the interesting part. We have words. In the documents, we have words, we have terms, okay, mostly meaningful words from the dictionary in any natural language. But in vector, we cannot multiply or take square or square root of the words. We need to convert the words into numbers. We need to convert words or terms into numbers. How to convert them into numbers? Okay, let's see. We have a very simple model for that. It is called TF-IDF, term frequency inverse document frequency. Now, a product of term frequency and inverse document frequency, it forms the component of the vectors, every vector. What is the concept between TF and IDF? Let's see. Term frequency. For term frequency, the idea is very simple. If there is a document in which a certain term appears less number of times, it should be considered less relevant to that term. If a term appears more number of times, the document should be considered more relevant to the term, right? Very simple concept. Like if there is a term, let's say system, it appears only one time in a document, and in another document it appears 100 or 500 times. Of course, the second document, it is providing you more information about system. The first document, it has only one occurrence. So the more number of times a term appears in a document, the more weight it should be assigned, the higher value it should have, okay? But higher value, but not necessarily linearly higher. Like if it appears one time in a document and in another document it appears 2 times, we cannot say this document is double relevant as compared to this. So to control this growth rate, there are many variations of the formula, but the one we use is we take logarithm of the frequency, like, and we add 1 to it. Okay, this is the formula we use if the frequency of term T in document D is greater than 0. If the term does not appear in a document, then it is assigned 0. For example, if a term appears 20 times in a document, we will have log of 20 plus 1. If it appears 1000 times, the term frequency value will be log of 1000 plus 1. Okay, so just to control the growth rate, we use logarithm of the frequency of the term t in document D, and we assign it 0 if the term does not appear in the document. Simple. The second component is IDF, inverse document frequency. Well, the idea of IDF is that there are some terms which are very common, which appear in almost every document, and they should not be considered that important. For example, we have seen that in the Shakespeare 37 plays, it appears like I think more than 28,000 times. Okay, so this is a very common term which appears many times in every document. So to discourage this these kind of terms, we introduce another measure which is called IDF, inverse document frequency. So it assigns more weight to a term which is less common in the entire document collection. Not talking about one document, we are talking about all the documents in the document collection. So N is the total number of documents in the collection. Like for Shakespeare, we have 37 plays, we have 37 documents. Maybe in one system we have 1 billion documents, in another maybe we have 10 billion documents, right? So how we calculate IDF? We divide the number of documents by the number of documents in which the term T appears. So NT is the number of documents in which the term T appears. So the higher value it will have, ultimately lower value we get for IDF. So if a term appears in few documents, it will be assigned a higher weight as compared to a term which appears in more documents, which is something like the, am. So these terms, they appear many times, so we assign less weight to them. We discourage the common terms. Okay. Of course, again I'll repeat that these are very basic formula. So of course their advanced versions, they are much more complex, but at a very basic level we make these rules in the vector space model. Now let's see how it works. Let's say this is our document collection. Okay, this is our document collection. Do document 1 contains do you qual sir no sir, if you do sir. Document 3, if you do sir, I am for you, and so on and so forth, right? Now if we want to calculate IDF value for sir, okay, IDF is log of n over frequency of sir. Okay, so log of n is the number of documents in the entire collection. So we have 5 documents, and f is how many times, how many documents. Actually it is not the frequency in all the total frequency, it is only the number of documents in which the term appears. Okay, so here frequency means we are talking about doc ID index. If I take you back to the previous slide, and T is the number of documents in the collection containing the term T. So let's say this document, one document like this document, it takes sir appears 2 times in it, but we will count it only 1. We will just count the number of documents which contain the term sir. So it can be calculated as log 5 over 4, because there are 4 documents which contain the term sir. Document 1, 2, 3 and 5. 4 does not contain. So there are 4 documents which contain the term sir. So while calculating IDF value, we will take log of 5 over 4. Total number of documents divided by the number of documents containing the term T. One important thing let me mention for you over here is that all the logarithms mentioned in these slides and in your book chapter, their base is 2. I'm sure you know about the base of a log. Okay, every log has base. So here this value, for this the base is 2. If you use calculator, in your calculator you have two types of logs. One is, we call it common logarithm, which is log, and the second is natural logarithm, we call it ln. So for common logarithm the base is 10, and for natural logarithm base is e. So if you calculate this with one of these buttons, you will get a wrong value. Okay, if you have on your calculator log of base 2, then use it to calculate the values, you will get the same value. If you do not have, let's say your calculator has only these two logs, in that case you can use the formula I have given on this slide. This is a formula for converting base of any value. For example, you want to calculate log, you want to calculate the value of log base 2 of, what is this, 5 or 4 is 1.25, 1.25, okay. And let's say on your calculator you only have log of 10. So by using this formula, how you will convert it to log base 2? What you will do, you will take log base 10 of what is x. So you want to calculate the value of 1.25 with base 2. So b is 2, x is 1.25, and on your calculator you have 10, so a is 10. How you calculate? So you will calculate log base 10 of 1.25 and divide it by log base 10 of b. What is b? b is 2. If you do this, then you will get 0.32. Okay, I hope you get it. If you have base 2 log in your calculator available, you can use that. If you do not have, then you can use this formula, and I mentioned you how to use it to calculate the values so that they are consistent. And I must emphasize over here that you can use any logarithm for all the formulas, for all calculating all the values, but you must use it consistently. Even if you use log base 10 or base e for calculating all the values, you should be fine, okay, but you should not calculate some values with one base and some with the other base. It is just to help you in matching the values when you are practicing. If you use log base 10, you will not get this value. If you want to make sure you get this value, you must use log base 2, right? So this is IDF for term sir, and now because sir appears 2 times in document 2, okay, in document 2 it appears 2 times. Now how we can calculate the TF IDF? This is TF log of frequency of sir in document 2 plus 1 in 2. This is IDF. So you get the value of TF and IDF and multiply them, and you will get the value. So TF IDF for this term in document 2 is 0.64. Okay, so in document 2 we will have a vector, and the component for the term sir in this document will have value of 0.64. I hope you get the basic idea. So this is how we convert all words, all terms into numbers in our documents. This is how we can convert the terms into numbers, and then we can process them further. So let's try to develop one document vector. Today inshallah we will develop one vector, and inshallah in the next lecture we will calculate a similarity of the document with the query vector. So let's say this is a document collection. Again we are talking about the same document collection, and we want to build a vector for document number 1. So in document number 1 we have 4 terms: do, you, qual, sir. So first, for do, how we can calculate its value? The first thing is to calculate TF, and the second we need to calculate IDF. So for TF, the first is frequency of do in document 1 is only 1. It appears only one time in this document, so frequency is 1. How to calculate TF score? Log of 1 plus 1, which is 1. Very simple. Again, this log base is 2. Okay. Although even for base 10 you'll get the same value, but it is base 2 over here. And to calculate IDF for term to do, n is 5. The total number of documents is 5. And in how many documents the term do appears? It appears in document 1 and document number 3. That's it. 2, 4 and 5, they do not contain term do. So the NT, this is basically NT, the number of documents in which term T appears, it is 2. So IDF, we can calculate log of n over NT and we get 1.32. Again, the base of this log is 2. So TF IDF for term do in document 1 is TF coming from here, okay, this value TF, and IDF, this value coming from here. So multiply value of TF and IDF and you get 1.32. It means the value for the component do in document 1 will be 1.32. Okay. Similarly, if I calculate the value of sir, the frequency of sir in document 1 is only 1. Okay. So it will be log of 1 plus 1, which is 1. And to calculate the IDF score, we can go back to slide number 25. Slide number 25. Yeah, we have done it over here. Okay. By the way, let me emphasize one thing for you to make your life easier. TF has a different value for every term in every document. Okay. TF has a different value for each term in every document. But IDF, it has only one value because IDF is a global parameter. So only one, you calculate value of IDF for each term only once, and then you can use it in all the documents, right? You do not need to calculate it for each term. Inshallah, you'll have an assignment. So just to save your time, please use this trick. Calculate the value of IDF only once for every term in your vocabulary, not for every document. Okay. So just like for sir, I have calculated it only once. I got the value of 0.64, so I can use it over here. IDF. Okay, sorry. IDF is 0.32. Sorry, it is TF IDF. So IDF is 0.3. I'm sorry. This is TF IDF, not this one. So the value of IDF is 0.32. So we can use it over here, 0.32. Now TF is different. You see, in the previous TF was here, log of 2 plus 1. So it comes out to be 2 TF for sir in document 2, because it appears 2 times, 1 and 2. So TF value will be different, but IDF value, it will be same. IDF is same. I hope you get it. So we use the same IDF, and now TF IDF for this term in document 1 for sir, it comes out to be 0.32. Right? Now how do we construct the vector? Now I believe you know that how we can calculate individual components. You can calculate TF IDF for do, you can calculate for u, for quer, for sir. I believe now you are able to calculate the individual components for each term in every document. Now how to put them in the form of a vector? The first step is to build a vocabulary list. Okay. So this is the dictionary, distinct terms in document collection sorted alphabetically. Make sure, this is very important. We pick unique terms in the entire document collection and we sort them alphabetically. So first we have a, then am, as, where, do, for, and so on and so forth, till the last term appears with y, which is you. Okay. So for every document, the components will be same order. Their order will be same, which means in every document the first component must correspond to a. The second component must correspond to m. The third component must correspond to as. Fourth will be the value of better, and so on and so forth. The last value will refer to u. Okay. Now in this document, in document 1, we have only 4 terms. We have do, we have you, qual, sir. One term is do, you, qual, sir. 4 terms. So for all the other terms, the value will be 0 exactly in the same order. So a, m, as, ber, all of them they are 0. Do has a value, you has a value, sir has a value, and qual in the same order. All the other values they are 0. Okay, so this is how we develop vectors. Once we have calculated TF, IDF scores for all the components, now we will use this same order, the dictionary terms sorted in alphabetical order. So this will be our order for all the document. Every document will be represented with the same components. First component is always referring to a, the last is always referring to u, and rest in the same order. So this is how we can make the vectors. If we here you can see we have developed vectors for all the documents in the document collection. For example, let's say I don't have to, okay, let's say document number 4. Document number 4 has only 2 terms, no, better. So in document 4 we have only 2 components, one referring to no, document 4, one referring to no, and second referring to better. This one. Okay, so I'm talking about this one, document 4. Okay, so it has only 2 components, 2 non-zero components. All the other components they are 0. And how these 2 components are calculated, we have just seen. We can calculate TF, IDF values, and we can we just multiply them to calculate the TF, IDF values. So today we have learned how to develop the document vector. Inshallah, in the next lecture we will develop a vector for the query, and we will try to calculate the similarity between the documents and query to rank them in the order of their relevance. So thank you very much. That's the end of today's lecture. Inshallah, in the next lecture we will continue with the vector space model to calculate the relevance of documents with a search query. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.